Okay. Okay, so welcome everybody, the people in the room here and the people joining us online. So my name is Andrew Dimmock. I'm a scientist at the Swedish Institute of Space Physics, which is in Uppsala, which is not far from here, in Angstrom, Alberta. And today we're going to be talking about something called the solar wind. So if you were here for the last talk, then now we're going a bit closer to home. So we're going to be talking about our sun, but mainly the sun's impact on Earth and actually how this impact can affect our daily lives. So we'll talk about what the solar wind is, how it affects Earth, and what type of effects we can expect from this thing called the solar wind. So we're going to keep it relatively simple. We're going to first start off by talking about what the solar wind is, where does it come from, what is it made of, and also then we're going to talk about some extreme kind of behavior that sun can give us. And this is when the solar wind can become a lot more stronger, and this is something called coronal mass ejection. And then, more interestingly, we'll talk about what happens when the solar wind reaches our planet. So what kind of interactions do we get? What kind of effects can it have on our daily lives? But more specifically, what can it affect our technology? Can it affect our communications? Can it affect our power supply? Can it affect satellites? These types of things. Because the behavior of the sun actually has an important role in these types of damages on our technology. And these are the type of things we'll try to look at as we go through this presentation. But I want to kind of start by just sharing with you some exciting new data that we're having, and this is from a mission called Solar Orbiter. So if you're not familiar with Solar Orbiter, it's a joint ESA and NASA mission, and it's a spacecraft that flies much closer to the sun than we've ever been able to go before. So it's looking at the solar wind much closer to the sun than we've been able to do up until now. And it's also able to look and take pictures and different types of measurements of the sun at much closer distances that we've been able to do until very recently. So this is a very exciting kind of new mission for solar physics and looking at the solar wind, because we're exploring an environment that we've not really been able to explore up until today. So IRF, the institute that I work for, we have some hardware contributions on this mission, and we analyze data from these probes that you can see just here. So Orbiter is taking measurements as the solar wind passes the spacecraft, but it's also taking measurements from cameras and taking remote measurements of the sun itself. And the idea is to have a combination of measurements where we put together the observations that the spacecraft sees, and then also what the solar wind the sun is doing at any given time. And I want to share with you this movie, and it kind of shows the extreme close-up videos and images that we're getting of the sun. So now we're looking at the solar corona, which is the atmosphere, the upper atmosphere of the sun. And we're able to go to this really remarkable close distance and see all these small-scale things on the sun and in the corona. And if we can zoom in on one of these pictures that they provide, we can see all these small magnetic field structures that are on the corona. And it's all how these structures behave and entangle with each other that is causing the solar wind, and also the kind of extreme behavior that we want to be able to predict and understand. And the solar wind itself is, I think I'd start here with just a basic fact sheet, just some basic information of what the solar wind is. So it's a stream of charged particles, so mainly comprised of protons and electrons, that are basically being emitted by the sun continuously, all the time. And space is almost nearly empty. So if you think, we only have in 1 square centimeter about 7 to 10 protons and electrons. So in just a small square cubic centimeter, we only have 7 or 10 protons there. Compared to if we think about the density of air, where we have about times 10 to the 19 molecules, so 19 zero. So we can think it's almost empty, it's almost a vacuum, but these kind of protons and electrons, they create some interesting behaviors and some interesting things. So although it's nearly empty, it's still causing a dramatic effect. And one important thing about the solar wind is it's extremely fast. So the average speed of the solar wind is about 400 kilometers per second, which then is equating to maybe 1 million kilometers per hour. So if you compare that to what you drive in a highway, which is 110, 120, then you can imagine just how fast this solar wind is traveling. But CMEs, so when we have these ejections of mass from the sun, these can propagate at much quicker distances, so maybe 5 times quicker than what the average solar wind is. And I'll show you what a CME looks like. But in general, they can reach up to 2,000 kilometers per second. So it only takes a matter of 1 or 2 days for these CMEs to reach us. And the sun itself has kind of a dramatic effect on our lives. One of the effects that we're used to in northern countries like Sweden, Norway, Finland is the aurora. So the sun's activity is directly causing the northern lights. And I'll explain how this works later on, but one of the negative aspects of the behavior of the sun is also that it can damage technology, both the satellites in space, but also the technology on the ground. So we have nice effects of the sun, such as the aurora. It creates this beautiful light show for us, but also it can have some negative effects, what we want to try and avoid and actually protect against. So these explosions that I mentioned on the sun, it's causing something called coronal mass ejections and also solar flares. But these two they can happen together, and sometimes they get mixed up. So solar flares in general are a type of explosion that releases X-rays and bursts of energy. And these release very fast moving energy that goes maybe to the Earth in a matter of 8 to 10 minutes. But CMEs, they're much slower, and they're also created by these large explosions. But the CME is a big blob of plasma that propagates from the sun out into the solar system. And these typically move anywhere between 400 kilometers per second up to 2,000 or even more. But most interesting thing what happens is when these CMEs reach different planets, so when it reaches Earth. Here we're just seeing some movies of what happens on the sun's corona when we have these solar flares and these coronal mass ejections. So you can see flares here. Usually they look like these really bright spots on the sun from these types of images. And then the coronal mass ejections, we can see we have this eruption and this big blob of plasma that just gets thrown out from the sun, and it propagates into the solar system. So this can either be thrown out close to in the same direction as Earth, or it can be thrown out in a different direction. But a lot of the times it's actually directed towards Earth, and it creates some interesting reactions. And this is when we tend to see the most strongest northern lights. So I'll mainly talk about the impacts from the coronal mass ejections when I talk about the space weather aspect of these types of things. So I thought it was interesting here just to show you what type of things we do as scientists and how we study these from a spacecraft. So we've seen these type of images that I showed on the previous slides, but also we have to think about, we have a spacecraft which is sat there in space, and then this blob of plasma, this coronal mass ejection will pass by the spacecraft. And it's just a single point. So what's happening is this spacecraft is carving a path through the CME. And on the right hand side here we can see some measurements that the spacecraft is taken. So this is actually measurements recorded by the spacecraft and then transmitted to us on the ground. And what we do is we analyze these measurements. So we can see when we have this coronal mass ejection passing, we have a large increase in the speed of the plasma, the magnetic field is a lot stronger, and the density is also stronger. So this 7 to 10 protons, electrons per cubic centimeter actually can increase to much higher. So we have a big change in conditions compared to what the solar wind is in its kind of normal state. And by studying this data here, we want to know how a CME works. So all these little kind of wiggles and changes in parameters here, we want to understand why these happen. But most importantly, what we want to do is predict when this will actually reach us. So it might be quite simple to think, okay, we have a speed, and we can calculate the distance, and we can see when it arrives. But actually, the speed can be changing quite a lot. And also, if the CME is not directed directly at us, it's very difficult to estimate this speed. And these things are moving so quickly, we even get a shock wave that forms just upstream of this blob of plasma. And the shock wave is just formed because this thing is moving so quickly. So we can kind of imagine on the Earth when we have an aeroplane that's moving very quickly and it's passing the sound barrier. We also have shock waves that are generated around this airplane because we have something moving very, very fast. And it's the same that happens with this blob of plasma that is kind of moving towards Earth as well. So what happens when it reaches Earth? So the Earth has an internal magnetic field, and in general the interaction between the solar wind and our magnetic field creates what we call the magnetosphere. And this is just a kind of easy diagram that shows what the magnetosphere looks like. So the solar wind is coming from the left here, and because the solar wind hits our magnetic field, it creates another shock. So we have shock waves, for example, upstream of the CMEs, and we also have shock waves just upstream of the Earth. And by upstream, I just mean the direction of the Earth that is pointing towards the sun. So the the day side essentially. And then we have a kind of compressed magnetic field on the day side. And then at the night side, we have a long tail that extends away from the direction that the Earth is pointing. And we call this the night side. And the CME, it creates some very interesting interactions between this magnetosphere and this blob of plasma that is kind of being ejected towards us. So you can imagine this is just the stationary state before one of these CMEs hits our magnetosphere. All these little lines here, these are just magnetic field lines, and it's just a familiar kind of picture of what we saw on this slide. So we have a north pole and a south pole, and the field lines are kind of emanating from these two different poles. But you can imagine when we have such a big blob of plasma with faster speed, higher density, large magnetic field, this very simple picture, it changes very dramatically. And what you're seeing on this kind of mover here is changes in things like the density, the temperature, the magnetic field orientation of the magnetosphere. And when we have all these changes, we get some very interesting things happen. One of the nice things is we have really bright aurora that we can see in mostly northern latitudes. But also, you can imagine if we have spacecraft that are inside all these interactions, then we can have very dangerous things happening, like it can damage the spacecraft, and also it can affect technology on the ground as well. So, as scientists, ideally what we want to do is to try and understand this complex behavior when we have this CME that arrives, because we want to understand when we can expect these damaging interactions with spacecraft, when we have damaging interactions on the ground that cause damage to power systems, all these various types of things that we can expect. But it's very, very difficult because we have very limited measurements to do these types of things. One of the most common kind of aspects of space weather, and I mention this term space weather a lot, but what I really mean in space weather is similar to atmospheric weather. So atmospheric weather is just conditions that are changing in our atmosphere, and these cause things like rain, they cause things like hurricanes, various types of things. And we want to be able to predict what the weather's going to be. Space weather, what I'm referring to here, is just changes in the conditions around our near-Earth space. So similar to atmospheric weather, we want to be able to predict when it's going to be, for example, very chaotic, or when it's going to be even calm. And one of the things which is causing aurora is actually space weather. So this tail region that I mentioned on the previous slide, it can actually, in some situations, it can act like a battery. You can store energy in this tail. And this is happening on extreme basis when we have these coronal mass ejections and it reaches the Earth. And we can see as we store energy in this tail, we keep storing more and more energy. And eventually we have to release this energy. When we release this energy, it's directed back towards us on the Earth at the night side. And because how our magnetic field is configured, and we have this kind of closing in the northern southern latitudes here, then all the particles that are released from this burst of energy, you can think of these field lines as a highway for these particles, and they'll travel along these field lines, and then they'll kind of start raining into these polar regions. So this is why we see aurora in the northern regions, because this is where the magnetic field lines are directed, and the particles are traveling along these field lines. And like terrestrial weather, where we get rain of just water, here we're getting rain of electrons on these high latitudes. And something interesting happens when you start having these electrons falling at these high latitudes. Well, we mentioned before that the density of this plasma is quite rare. It's only 7 or 10 protons sometimes. And in this tail region, we can actually have only 1 proton per cubic centimeter. But these electrons, what happens when they get down to our ionosphere is they suddenly enter a region and there's a lot of stuff there. The density increases dramatically. So where we don't have collisions between particles in the solar wind and in our magnetosphere, we start having collisions in the ionosphere. And the light that you're seeing from the aurora is actually due to these electrons that are hitting these atmospheric neutral atoms in our ionosphere. And then it causes a chemical reaction that emits light. And this is what the aurora is. It's just electrons that are colliding with these atmospheric neutrals. And we get aurora in different colors because it depends on what type of neutral the electron will hit at any given time. So this is why in different conditions you'll see green aurora, you can see red. So it can create aurora of different types of colors. And in very, very strong conditions, like we see on the picture on the right here, we can get multiple colors at a given time. So it creates a very kind of beautiful light show that you can even see at even more southern latitudes when we have stronger space weather even sometimes in Uppsala. I think in spring this year we also had some aurora in Uppsala. So the stronger we have space weather, the more southern we can see the aurora. There's some famous old space weather events where you could see aurora even down to places like Italy and things like this. So really extreme space weather can cause aurora to go extremely southern latitudes that we wouldn't normally see it. And we can usually do a good job of predicting where we'll see aurora. So there's certain websites, certain places you can visit which will tell you at what locations and latitudes you would expect to see aurora. Sometimes with 1 day lead time, sometimes a little bit shorter, but usually you have to go somewhere very dark. So if it's cloudy, you won't see the aurora at all. But if it's a clear sky, if it's dark, and we have some space weather activity going on, then you'll see aurora. If you want to definitely see aurora, space weather is the safest bet is to go to Kiruna, somewhere like this. That's really high latitudes, because then we get aurora all the time. We don't need such kind of strong space weather to see the aurora at the really high latitudes. In Uppsala, we have to be kind of lucky. Expect we have a clear day and that we have some kind of activity going on in our near Earth space. But aurora is just one type of space weather. It's a nice type of space weather. It doesn't harm us. It creates really nice light show for us. But one important thing to mention here is that space weather has a very kind of array of different effects that it can have for our daily lives. So aurora is just one. But for example, if we have an astronaut that's out doing a spacewalk or something like this, then we can also have harmful radiation that can cause actual damage to the astronaut itself. So this is another aspect that we want to be able to avoid. And other things is we can have errors on GPS signals on the ground, and we can have even some risk to radiation for passengers on when they're on high polar flight paths. And another important effect from space weather, which in Sweden we really do a lot of research to understand, is how space weather can affect our power systems. So what happens when we have really extreme space weather is our power system we can actually have new currents that go into our power system, and it can cause blackouts and even damage to things like transformers in the power systems itself. So this is something in Sweden and at high latitudes we're quite susceptible to, because the atmospheric currents that are causing this type of behavior are much stronger at these latitudes. So this is something we need to avoid in terms of predicting when it's going to happen, but also designing our technology so it can handle these kind of different effects. And then there's other things such as radio communications and all these different types of things. So it's a big field of trying to understand all these different aspects of space weather and trying to predict when they'll happen, and also to mitigate and protect our technology against these type of effects. But as we showed in the last talk, when we had these supernovas and these kind of astrophysical phenomena, things that are going on in our solar system, it's not so far removed from these type of distant objects that we're studying with astronomy. So I mentioned at the Magnetosphere we have a bow shock, a shock wave formed by the interaction between the solar and our magnetic field. We have shocks that are formed in front of a CME. But then we also have shocks, for example, when we have exploding stars, some supernovas. And there's a direct link between the physics and behavior of what's happening at these shocks in the solar system and also from these exploding stars. So there is a direct link between the space physics that we kind of study in our solar system and also what the astronomers are doing by these really far away distant objects. And one of the things is we want to understand how these shocks actually work. They're very complex phenomena themselves. So here we're looking at a supernova remnant, and this is in a non-visible spectrum. So it's different colors are representing different types of material there. And this is moving very, very quickly, so even quicker than the CMEs. So what we want to do is try and relate what we see in the heliosphere closer to Earth to these types of objects. And the reason this is important is because the shocks in the solar system are the only ones that we can actually go and put a spacecraft inside the shock itself. So these type of things that are really far away, it's just too far to spend money to spend spacecraft there. We can't even reach these types of things, so we have to use remote measurements to study them. So this is the challenge, is to kind of understand how all these things in the astrophysical environments and also in our solar system, how they all fit together and the differences between them. So just some key things to remember. There's a lot of kind of things here to remember, so I thought I'd just put some key points here. So explosions on the sun cause these coronal mass ejections. And it's these coronal mass ejections that are causing the most extreme type of space weather that we experience on the on the Earth, both in terms of what the satellites experience and the damage that they can endure, are also damage to our ground technology. And the solar wind and coronal mass ejections are very fast, so they're moving a million kilometers per hour, and they take a matter of days from the sun to the Earth. And there's some nicer aspects of space weather, such as aurora, but the other side, there's a more concerning aspect of space weather we want to kind of avoid. And one important thing to take away is that you'll see some astronomy talks here, but when we talk about space weather, when we talk about the sun, our kind of inner heliosphere, there is direct links between astronomy and our space physics. So as scientists, we're always working together to try and understand and bridge these gaps between the solar system and then things which we see really far away. So thank you very much, and yeah, I'm happy to take some questions. Yep.
1 second. There you go. Also? The solar wind, is it? I've seen some like articles about ideas of using it to propel spacecraft. Is that something that you think is going to happen?
There are some ideas about propulsion using the solar wind, but I don't think eventually it could happen. But I don't think right now it's seen as kind of a reliable way to propel spacecraft. But I think it's definitely being looked into, because especially if you want to go to Mars and these types of places and you get exposed to this radiation that's coming from the sun, then we had to add master spacecraft for shielding and things like that, which costs a lot of money in terms of actually propelling this mass. So if we can do that with just using the solar wind, for example, there's things like solar sails, then it would help in that way. But I don't think it's been. I think there's some test case situations with CubeSats, very small spacecraft, but in terms of like a viable engineering solution for a large spacecraft, I don't think it's quite there yet. But there's a lot of ideas about how this could be used. Thank you.
Thank you very much. A question. You write here, we have shock waves in the solar system and far away from explosions. But what is the shock wave? Is it in the gravitational field or particles or something?
Yeah, so this is a very good question actually. So the shock waves in space, especially in plasma, it's very different to the shock waves that we have on the Earth. So we call this a collisionless shock. A collisionless shock. So it's the interaction with the electromagnetic fields and the particles that cause the shock. So when we have for example, when we have an aeroplane moving quickly on the ground, we have a lot of collisions that are responsible for a shock. And this is the way that the shock can exchange energy and kind of keep itself in its form. But if we calculate the kind of the length that a particle has to go to collide with another particle in the solar wind, it's about the distance between the sun and the Earth. So inside these shocks, we can pretty much ignore any collisions between any particles. So the only thing left to kind of control this kind of conversion and dissipation of energy is actually just the interaction between the magnetic and electric fields and the particles themselves. And if we zoom in these shocks, we have a very complicated structure. So it's okay, yeah. Okay, yeah. Shocks are a very fascinating phenomenon because they happen everywhere. And it's actually a very useful kind of way of comparing different environments. So we can compare shocks on Earth, we can compare shocks at supernovas, and we can compare shocks at CMEs and things like this. And of course, the Mach number of these shocks is also changing a lot as well. So it's really interesting physics what happens when you get, for example, these supernova remnants and the Mach numbers can go really high. The physics becomes quite interesting. So yeah, it's the shocks kind of, they work quite differently, but it's a nice way to compare between different environments.
Any more questions?
Is there any further expeditions? I mean, like the solar orbiter. Is there any? Is it? Are we going to send another spacecraft that's going to go even closer? Do you think?
So we have also measurements from another spacecraft called Parker Solar Probe, which is also a similar mission to solar orbiter that's flying close to the sun. The difference between Parker Solar Probe and Solar Orbiter is mainly some small differences with instrumentation, but also Solar Orbiter eventually it's going to lift its orbit so it goes to the polar regions. So we can look at places of the sun we've not really been able to look at before. But in terms of going even closer, I think the problem is also an engineering problem as well. Is the sun is very hot, so we have to have a big heat shield and have all the instruments kind of hiding behind this heat shield and trying to keep the spacecraft running, basically. So I think there's also always a demand to go even closer. But I think at the minute, I think these two missions they're still in their main science phase. So I think I don't think there's any immediate plans to go even closer. Well, these spacecraft should be going for quite a few years. And once these nominal mission phases are finished, we've got a bigger amount of science return, maybe we can get a bit more risky with the orbits and maybe think about going even closer if we can. And we did this with some other missions, such as Venus Express. When it was operating at the end of the mission, we crashed it down into the planet, so we could take measurements even closer. So there's things we can do, but yeah, it creates a quite big engineering challenge to go so close.
It seems like we might be out of questions. Well, then I want to thank you very much for this wonderful presentation.
Thank you.